Um, Jinja asked me to give a talk on resonance fluorescence Lidar, so she gave me this topic and I made the outline something like this. So I will give some introduction about metals in the elemental region, like why and how they occur, and then I will discuss little bit about the resonance Lidar technique, in which I will introduce some equation, but Lidar equation has been discussed so many times. So I will just focus on how we derive densities from the resonance signal, and I will discuss briefly about what is the significance and a brief history, and then I will give some examples about different metals, showing the distribution and characteristics of different layers, emphasizing on the multi-metal measurements from various latitudes, and how temperature and chemistry can affect different metals, and then in the end just summary. So this actual elemental region has two main characteristics. One is the low temperature. Geospace showed very good examples of double mesopause, and the low temperatures are caused by three different reasons. One is like there is lack of sufficient heating, because most of the UV extreme ultraviolet radiation is removed in the thermosphere, and then in this region the pressures are very low. So there is lack of formation of the ozone, which is the main mechanism in the stratosphere for the absorption and causes the high temperatures there. And because of this low pressures, the greenhouse gases like CO2 can act as infrared radiators, and that can contribute directly to the cooling of this region. And the other characteristic of elemental region is the occurrence of metallic layers, and this actually shows like the meteor input. So what causes the metallic layer? There are two important sources that results in the metals, or that deposit the metal, which is due to meteor input, and there are two sources of meteor input. One is the comet. So the dust rays, when the comets sublimate as they revolve around the sun, causes, like, they are responsible for the meteor showers like Leonids and Perseids, which are very famous. And the other one is the fragments from the asteroid belts beyond Mars, and they are responsible for the sporadic meteor input, which gives the meteor, or the, I would say, which is responsible for the major metals in the elemental region. So these metals they act as tools for studying or probing the elemental region, as we have seen earlier too in the case of the sodium. So the source wavelength has to be, the source can be either air glow or the laser, and so if the source wavelength is tuned to the atomic transition or the specific resonance wavelength or certain metal atom that we want to study, and then the return signal scattered photon is received by a telescope, that is the Lidar, so we can study different metals. So historically, air glow was the way, or historically if you look, then the existence of the sodium atoms were first discovered using twilight air glow emissions, and the first Lidar observations were made possible when the laser technology improved, and it was done by using a dye laser which was formed by a flash lamp. However, this limits the long-term measurements, because the high energy of the flash lamps will just shorten the lifetime of the dyes. So later on, with the development of the laser technology, people used dye lasers that were pumped by Nd:YAG lasers or excimer lasers, and that resulted in long-term observations. Some of the observations span at least a solar cycle, and two such groups are the Clementius group from southern hemisphere and Geospace groups from the northern hemisphere, that have provided a very long-term sodium data sets. So potassium, calcium, and other metals that were first studied were from the French group, and these measurements were made individually, but later on simultaneous observations were first made by Illinois group, and then Ca plus measurements were made simultaneously, also simultaneously at at the IAP group, and Alpers et al. Reported some case studies, and later on Girding et al. Gave us a very good seasonal variation of Ca and Ca plus. So I'm not going into the Lidar equations. We should see how the densities are derived from the resonance signal, but we have looked at this equation many times. This equation actually it gives the total photon count. So by subtracting the background, we get the densities, which is this and z. So we can get the densities. However, if you look at this expression, the densities here depends upon the atmospheric transmittance and also on the power of the laser. So if there is fluctuation in the atmospheric transmittance and the power laser is also changing with time, pulse to pulse, then we do not get an absolute measurement. So to remove this problem, what we do is like we take the Rayleigh signal from an aerosol free region, which is generally 30 to 35 kilometers. So from this region, we derive the Rayleigh counts. So this is the expression for the Rayleigh photon count, and then we know the atmospheric density. So we normalize the photon counts from the resonance signal to the Rayleigh contribution to the Rayleigh signal from 30 to 35 kilometers, and we get the absolute densities. So the measurement accuracies depend on the total photon counts in the profile. So if you look at this expression, the total photon counts depend upon the atmospheric transmittance and also on the total abundance of the layer, and they also depend upon the power aperture product. So if some of the metals have the abundances which are very low, so if you need to improve signal to noise ratio, you really need what Andrew suggested, Uber laser or a very big telescope, so that you have a good power aperture product. So if you want to study different metals, you need to generate different resonance wavelengths. So one way that's what we do at Arecibo is like we have a YAG laser. Now we have 2 YAG lasers. So we use the YAG laser to pump a dye laser, and we use some particular dye to generate the dye wavelength such that when it is mixed with, when it is some frequency mixed with the residual from the YAG laser using a KDP crystal, then we can get different wavelengths. So if we are using say LDS dye, we can generate 423, or if we are using rhodamine dye, we can generate 372, which is the resonance wavelength for neutral iron. And for doing sodium, we can just directly pump the dye laser from the second harmonic of the YAG laser, and then we get sodium. Of course, we have to change dyes whenever we make a new metal measurement. So this is a little bit of time consuming, but it's worth doing it, as you will see later on. So why do we do all these metal measurements? There are many reasons for doing it, and one of the important reasons for doing simultaneous measurements of Ca and Ca plus is because, like if you look at this plot, which shows the variation of the chondritic abundance relative to sodium of different metal versus their column abundances in the MLT region, we see that most of the metals fall on this straight line. However, neutral calcium is highly depleted. It can be like by a factor of 10 to 50 to 100 lower than sodium or other metal. So what is the reason for this? We need to make observations of Ca and Ca plus, and one of the reasons Ca is important because Ca plus is the only neutral species whose ion can be absorbed from the ground. All other metals have their ions that have resonance wavelength deep in the UV, and they are absorbed heavily by the ozone. So they are not possible from the ground. We will need a space-based Lidar for making or observing other ion species using Lidar. And other reasons are like, do all the metals behave in same way? What are the factors that influence layer structuring? What is the latitudinal difference in the distribution of the different species? And how are neutral and ion species coupled together? These observations are important to develop models because we can constrain certain parameters in the model if we know what are the composition or what is the electron density or what is the ion concentration at a particular place. So, an example of ion and neutral coupling is illustrated here. So, this picture has been taken from Girding et al. Because they did lot of Ca and Ca plus measurements, and one of the advantages at Arecibo is that we can get the electron density measurements from incoherent scatter radar. And Ca plus of course we can do from using the resonance lidars at Arecibo or at any other place, and you can see the chemistry is kind of very complex. So, I am not going into the details, and this one shows some very recent simultaneous neutral calcium ion and electron density measurements that were made from Arecibo on 21st June. So, the interesting thing is that like we see this is the sporadic layer. When I say sporadic, it means like the layer is not always present there, it is kind of sporadic in nature, and you can see that sometimes there is a sudden increase or enhancement in the density. So, these are called as sporadic E layers when we talk about electron density, and if it is a neutral layer as in the case of neutral calcium, we call them as sporadic neutral. So, you see that there is complete absence of neutral calcium before midnight, but when there is an increase in electron density, we see some increase in the neutral calcium density. This is because like our power aperture product is not very good at Arecibo, so we do not see if the calcium is very weak, say is around 1 or 2 atoms per cc, our system is not going to detect it. If the conditions or the sky conditions or atmospheric transmittance is not good. So, as I said that different metals behave differently. So, this is an example of sodium and iron. Iron is one of the abundant species in the MLT region. So, there is a sporadic layer in the electron density. There is an equivalent sporadic layer in the neutral sodium data, but we do not see that increase. There is a very weak layer. I will not say that it is sporadic neutral layer because its density is almost same as the main layer. When I say main layer means the metals that occur between 80 to 95 kilometer, that is the main layer, and if there is a enhancement beyond that, that is the sporadic layer too. So, there are different ways of defining sporadic neutral or sporadic E layers. So, again discussing about the characteristics of the layers, I am showing the example of neutral calcium and potassium. So, we have another laser at Arecibo, that is the Alexandrite laser tuned to the resonance wavelength of potassium, and my colleague Jonathan Friedman runs this system, and this can also give temperature measurements. So, here there are two important things that I would like to point from this slide. So, if you look at the top side layer, so you see a very strong increase in the calcium density. There is a very weak layer in the potassium at higher altitudes. However, the main layer, which is like between 80 to 90 kilometer regions, shows the opposite behavior. It is stronger in potassium, and this one is weaker in neutral calcium. So, this is like kind of a opposite behavior, and I would go to the top side behavior after this. So, the thing is like this might be due to the chemistry and dynamics, but I am not going into that details right now. So, the top side layers, when we see on the shorter time scales, they showed that they were very different in the two metals. However, if we look at the seasonal distribution of these metals at different latitudes, and this is the logarithmic scale. So, this is very important that we are plotting the seasonal distributions on the logarithmic scale. So, we see that on the top side, this is the data from the Kullinsprong, these two, and this is from Arecibo. And this has been published by Hoffner and Friedman. So, if you want to look into details, you can look in this journal. So, what I am going to show here is during the summer time there is an enhancement, or there is some enhancement very weak, like it is only 1 or 2 atoms per cc, which is seen both in calcium and potassium data, and the features are very same in the summertime. However, the main layer is different. So this is an opposite behavior as compared to the when we look at the smaller time scales. But at Arecibo, there is an extension too, but this feature is little bit different from the one that is seen at the higher latitudes. And so they tried to explain this in terms of the meteor showers. So these vertical lines basically show the meteor activity, and there is no correlation between the meteor activity and this topside increase in the density. So this might be due to some other dynamical process. One needs to look into this. This is still not understood completely. So as I mentioned, the main layers are very different, and they behave very differently at different latitudes. So I'm showing an example of the annual variation of neutral iron, which was done at Arecibo, and comparing it with that at a mid-latitude site, and has been reported by Kane and Gardner from Urbana. So this blue line shows the annual variation of the RMS width of the neutral iron layer at Arecibo, and this black line shows the RMS width of the neutral iron layer at Urbana. So there are two interesting things. One is the width ratio, summer to winter ratio. At Arecibo, it is higher than Urbana, and also they are anti-correlated. So the reason for this, if you look at the reaction, because the layer width will be determined how fast neutral iron is being lost from the MLT region. This can happen if the iron converts into a stable molecule with a longer lifetime. So it is not available to the lidar. Lidar cannot see it if it is in some stable form. So the layer width will decrease, and this temperature, this reaction depends upon the concentration of oxygen, and also it has an inverse temperature dependence. So we look at the distribution of the oxygen molecule at 2 latitudes and at 2 different altitudes. So this solid line shows the oxygen distribution at 18 degrees, which represents Arecibo, and the dashed line shows the distribution of O2 molecules at Urbana, which is at 85 km 2, and this one is at 90 kilometers. So as you can see, they behave very differently. It's an opposite behavior at 85 kilometers. So the smaller widths during summer at mid latitudes can be due to the cold mesopause temperatures and increase in O2. And as we know that the temperatures are colder, means the MLT region is the coldest region in the atmosphere, and so the warmer temperatures along with O2, less O2 at low latitudes can slow the removal of the neutral iron, and hence it will cause broader widths at Arecibo. So the effect of temperature is also seen in different ways. So one of the other consequences of low temperature on the metal layers is the growth of ice particles. So when the particle size, when these particle size they grow and their radius exceed 20 nanometers, they are visually observed as NLCs or noctilucent clouds, and they can also manifest in the form of strong radar echoes. And the first evidence of the link between the ice particles and the metal layers was seen from the South Pole data. So this picture actually shows some NLCs, and it has been published in JGR by Bikwar et al. 2002. The reason I'm showing this picture, even though there are better pictures from IAP, is because I wanted to show that these NLCs can be observed as low as latitude as 42. It's 42 degree north for Utah. So this is an example of PMC removing the neutral iron from South Pole. So this iron is basically eaten away at this point where we have these ice clouds. However, a different kind of behavior is seen at other latitude when we look at the distribution of potassium at Spitsbergen. So this figure shows the distribution of potassium layer from 78 degrees north, and the yellow contours superimposed are the distribution of potassium layer from IAP, which is Coulomb's bond at Coulomb's bond 54 degrees north. So you can see that the potassium atoms are removed more at high latitude as compared to lower latitude like 54 degrees north. So we try to investigate if it is really caused by ice particles or some other factors are responsible for this. So in order to see quantitatively the effect of ice particles on metal layers, we estimated the volumetric surface area using PMSE data, which is polar mesospheric summer echo data from radar, and then used a model, potassium model from John Plain. And one of the interesting things that came out was that the model can reproduce can reproduce these correct values of the potassium layer at Spitsbergen if the uptake coefficient as well as vertical winds are taken into account. If we decrease the uptake coefficient by factor of 10 and 100, then we are overestimating the layer, and if we are decreasing the vertical winds, then we are underestimating the layer. So the conclusion is this distribution is basically caused both by vertical winds as well as by the loss of potassium atoms due to the ice particles. So ice particles can have different effect on different kind of metals. So one of the interesting studies in the future will be to see how different metals behave at these high latitudes, because if you look at this plot, which shows the hemispheric differences in the PMC altitudes, you will see that the altitude of PMC is different at northern hemisphere and southern hemisphere, which was attributed to the differences in solar flux and mean flow driven by gravity waves. So this would be, I think Jinzhou mentioned me that this work is under progress and they are seeing some interesting results in iron distribution.
Yeah, we have the seasonal climatology from both South Pole and Ross. So for me, it's only the southern hemisphere.
Okay. So you need to do at northern hemisphere too. So thanks for your attention, and this is the summary of the entire talk.